Today we are going to continue our discussion about the magnetic field. So before we start, I would like to share a verses in the Bible, in the book of the Psalms 28 verses 7. The Lord is my strength and my shield. In him my heart trusts, and I am helped. My heart exalts, and with my song I give thanks to him. I know this is the first week of online courses, and everyone as a student and me as an instructor, we are all adopting a new approach, and it is definitely not an easy period of time for all of us. And also, I know that everyone, including me, we have probably stayed at home for almost 1 week. So I will continue to pray for everyone. But I also want to encourage you that during this difficult period of time, we should also pray for each other and pray for people who get infected by the coronavirus, and also for the people who are still healthy but they lost their job. And also, we should also pray for the wisdom of our authority of the country. Hope that they can guide us and lead us to go through this dark period of time, and everyone can go back to their normal life again. So, in the previous lectures, we have studied about the concept of the magnetic poles. So, the behavior is very similar to the electric charge. The only difference is you never can find out an isolated north and south poles. And each of the magnetic poles can produce a magnetic field, and they will interact in between them and produce a magnetic force. So please don't confuse yourself. The concept of the field and the force, they are completely different things. Then we studied about the magnetic domains, and when we studied this one, the movement of the electrons plays a very crucial part. And later on, we find out that if you have the electric current, which is the movement, the directions of the positive charge, then if you have this kind of electric current, they will produce a magnetic field. So here I want to remind you that when people talking about the current, we always assume this is the direction of the positive charge. But you may ask, how about now it is a particle with a negative charge moving? Still, they will produce a current. But now the direction of the current is in the opposite directions of the charge movement. So for example, if the negative charge is moving to the left, and the current produced by this negative charge is to the right. So I want to also remind you that now, start from the chapter 7, you will find out thinking about the movement of electron will be a very useful pictures when you try to understand about the temperature, the concept of temperatures, the concept of electric field, and the magnetic field. Today we are going to study in the opposite way. Now we are going to study that if you have a moving charge in the magnetic field, what will happen? And people find out that they also experience a magnetic force on that. Then we are going to study about the electromagnetic induction, which is something most of you will find out a little bit challenging. So today the lectures, we are only going to focus on these two topics, so which means that they are not an easy one. So let's try to refresh our memory about what we have learned in the previous lectures. So if you have the long wire current, and let's assume now first the current is moving from the bottom to the top. So if this is the direction of the current, then they will produce a magnetic field surrounding around the wire in the counterclockwise directions. However, if you reverse the direction of the current now from the top to the bottom, then you will produce a clockwise direction of the current. So, depending on the direction of the current, the magnetic field produced, sometimes it is counterclockwise, sometimes it is clockwise. So the direction of the force and the magnetic field are the most challenging part of the chapter 9. People will usually just get confused. So I would suggest that every time when you looking at this lecture note with my explanation, but you still cannot understand, you can pause the video, you can read the textbook or other reference if you want, or just repeat simply about the lectures. I hope that this one can help you to understand the material better when you try to move on to the next slide. So today we are going to study about the force experienced by a moving charge. So where is the magnetic force from? So here you have the U-shaped magnet, and here is the North Pole, here is the South Pole. So we know that the directions of the magnetic field is from north to south. So this is the directions of the magnetic field. Now you provide an electron beam moving from the left to the right. So that's the reason I say the beam is moving to this direction. However, you should be very careful because the direction of the current is in the opposite direction of the electron beam. So therefore, the current is moving in this direction, in the opposite direction of the beam, which is also perpendicular to the magnetic field. And people find out that this wire passing through the magnet field, they will experience a force, and the force is upward, which is simultaneously perpendicular to the current and the magnetic field. And people also find out how big the magnetic force depends on the angle between the magnetic field lines and the current. So they find out when the current and the magnetic field are perpendicular to each other, the force is biggest. So this is not I would say probably the first time you learn this kind of concept. The force also depends on the angle. And also, it is very important is you will find out the magnetic force is perpendicular to the direction of the particles. What does that mean? It means that this particle will not be accelerated by the magnetic force. So you will say if a force acting on the particle and has no interaction about the velocity, then what will happen? So I just say that the particle will not be accelerated, but the force, magnetic force, will change the directions of the charged particle. So that's the reason I say this is the deflecting force. So you will see more clear picture in the following slides. So let me help you to first try to help you how to decide about the direction of the force. This is the so-called right-hand rules. So this is the directions of your charged particles. So the right-hand rule is very similar to the approach I teach you last time. You should use the 4 fingers of your right hand. So you should point the 4 fingers along the direction of the charge and curl your finger toward to the direction of the B field. So direction of the current, and curl your finger to the B field. Then the thumb, when you curl your finger, the direction of the thumb will be the direction of the force. That is how we decide the direction of the force. So let's take a look about the previous pictures. So now you have the current moving these directions. So you should point your 4 fingers in these directions. Then you curl your fingers toward to the direction of the magnetic fields, and you will see the force is actually the direction of your thumb now. So please give a check. This is a very important thing you should learn today. So I just teach you how to determine the direction of the magnetic force for a moving charge in the magnetic field. So now if I give you this simple test, so here I give you the direction of the current, and I tell you that the force experienced by the current is upward. Then let's try to give a try. using the right-hand rule to determine the poles of the magnetic fields here. So once again, this is the forefinger of your directions. Your forefinger should point along these directions. And this is the direction of your thumb when you curl your finger. And you will find out, in order to produce an upward force with the current moving from the left to the right, you will have the north pole here and south pole here. And let's give a check. So the forefinger is the directions of your current. Then you curl your finger to the direction of the B field from this is north pole and south pole, so the direction is this way. So curl your finger to this way, and you will find out that the thumb is upward. Okay, so that is how you determine now, with given the information of the direction of the current and the force, then you can find out now the direction of the magnetic field. So now let's give one more test about this one. So you have the current moving in opposite direction, but now the force is downward. So please give a check again that now point the forefingers of your right hand now to these directions, and now the thumb should be downward. Therefore, you will find out still the direction of magnetic field is north pole here and south pole here. So this is the first right-hand rule you should learn today. And in our daily life, the magnetic force actually can be applied easily to a lot of different kind of facility, which you never probably think about that before. So let's try to think about that. If you could create a device. So in the picture I'm going to show you here is a train moving. So if the magnetic force acting on the train upward is equivalent to the mass of the train, what will happen? It means that the train can now moving along the track, but actually floating above the track. So if there's no physical contact, then there's no frictions and no vibrations. Then in that case, you can try to accelerate your train as fast as you could, if possible. But for sure, we will still have the air frictions and all other factors. But at least you already minimize the force against the direction of motion. And in that case, there's also no vibration because they are basically floating in the air. And this kind of concept is the so-called magnetically levitated vehicle. And now let me give you an explanation. So for this kind of the maglev train, at the bottom of the train, they have the south pole at one end and north pole at the other end. So you can basically say that I'm building the bottom of the train with a very big magnet. And now next to the track, you can say the side of the track, they also has a very big magnet embedded within that. But you should be very careful when you decide that. For this side of the track, it is a north and south pole. But on the other side of the track, it is opposite directions. Why we are going to do that? Because you will find out that if you have the south pole here and south pole here, they don't like each other. So there's a repulsions. And the south pole will be attracted to the attractions. And now you have two forces acting on the left-hand side of the train. So now the total net force is upward. But since you never can find out the isolated magnetic poles, so definitely on the opposite side it should be north. That's the reason you should have the opposite direction of magnet. So once again, the net force of the magnetic force acting on the other side of the train is also upward. So therefore, the train will experience an upward magnetic force to support the weight of the train, such that they can basically float along above the track.